Welcome. We thought we'd make a few introductory videos to describe the Grym, the R implementation of the generalized yield model. This video is just going to talk about some basic underlying principles. And I apologize if this comes across, I don't mean to be particularly condescending. It's just that I don't really know what everyone's background is. So I'm just going to try and go back and cover the basic principles. I hope you don't find this too laborious. So we're going to focus on principles here. And if you think about any age structured model, you sort of have time progressing this way. And if we have age progressing this way, essentially individuals are recruited, and as they progress forward through time, they progress forward through age. So you kind of have cohorts that move through time and age like this. And if you look at any particular year, you essentially see the progression of various cohorts through time. So individuals are recruited here, they grow older. Invariably in a model like this, there's got to be some upper age limit. So you might get to the age of, say, 33 and something quite unfortunate happens and you die. So we either have an upper age limit, and the assumption is that basically by the time animals reach that age, they've effectively all disappeared, or we have what's called a plus group. So these ages here, you can imagine this is sort of 18, 19, 20 years old, but there's an age here that's sort of meant to represent, say, 33 and older. And so this figure kind of needs to be modified a little bit in that you sort of recruited, you progress forward in time, and then you stay in that plus group. Once you get to 33, you stay in the 33 and older age group. In the model, we work year by year. So the core currency of the model are these matrices. And if you sort of think of the columns of the matrices as representing age classes and the rows representing times within the year. So there's kind of rows here. These represent time increments. Okay, so these are age classes, and this is time within a year. And if you want to think about these columns, they're really these trajectories here, but now I'm sort of drawing them vertically. And we have time increment within the year. So suppose your time increment was a day. One important thing to recognize is that this time would be midnight before the first day. The next time is kind of midnight at the end of the first day and preceding the second day. And so this time at the end is actually the time after the final day. So if you had daily time steps, and let's forget the complications of leap years, suppose there's 365 days, there's actually 366 rows in this matrix. And at the end of, so here an animal's sort of recruited to the fishery, grows through the year, and then at the end of the year, essentially that time point is equivalent to this time point in the next year. It's kind of like you grow to the end of the year and then you're sort of promoted to the 0th time in the next year, and you've sort of been promoted into the next age class. And similarly, these guys move to the next age class and so on. Now, there's an important reference point here. This initial time is essentially the time we assume that the population spawns, right? So this is essentially the 0th day of the year, where the year is aligned to the spawning. We don't necessarily, though, require that this first column be age 0. You know, the second column's age 1. You're quite free to make those age columns anything you like. You might have no awareness of the individual before age 3. You know, you might just have no data on that. So rather than force you to model those initial years, this first column is essentially the year or the age at which the individual is recruited to the fishery. That doesn't necessarily mean age 0. It might mean that you just don't know anything about these things until age 3. And that's fine. You just have to be sort of aware of that and be a little bit careful. So these matrices, these data structures are sort of key to the internal operation of the Grym. A lot of data is stored in this format. Matrices with rows for time, columns for age classes. And probably most importantly, we have abundance, which we call N, biomass, and yield, right? So abundance, the number of individuals in a particular age class at each time point through the year. The biomass is the sort of the combined mass of those individuals. And the yield is sort of the cumulative catch to that point. You know, so the yield for, you know, this third column here would be sort of, if this was age 2, you know, this point here is the total catch to this point in time during the year for that age class, and that's the yield. Okay, so that's kind of the key data structure. We project over a single year, and it's sort of we provide facilities for doing this, and it's kind of your job as the scripter to store that data and analyze it as you like. So, you know, we provide a function that projects over a year. You have to do the multiple years of projection. We'll sort of talk about this stuff in a subsequent video. Okay, so there's some sort of key things we need to provide to do a single year projection. One of the simplest things, you can imagine that we could make one of those matrices, and I'm just going to draw them as rectangles now, that just has the ages, and it's pretty obvious. You know, it's got columns for age classes, time points during the year. So you could sort of imagine, you know, the 2-year-olds, you know, if this is the column for the 2-year-olds on day 60, all this matrix is saying is on day 60, the 2-year-olds, they're 2 years and 60 days old. Right? But it's just a matrix of ages. You can imagine then, or certainly in the original generalized yield model, and we've kind of built the Grym to reflect, you know, it sort of reproduces the actions of the generalized yield model, which was originally implemented in Fortran. So in the original generalized yield model, that would then get translated to a matrix of lengths, which I've called L's, and a matrix of weights, W's. And so in the original model, we'd use a von Bertalanffy growth model of some form or another to take ages to lengths, and then there'd be a power law model that would take lengths to weights. And so essentially, you know, this would be the age of someone from the second year class on day 60. The corresponding point over here would be their length, and the corresponding point over here would be the mass of an individual in age class 2, day 60. Of these matrices, in the original GYM model, the generalized yield model, these were all created, and you would give parameters that would control how each was calculated from the other. In the Grym, you actually only really need to provide this. How you get that matrix is up to you. You can use von Bertalanffy growth, you can use power law, weights, or you can just dream up whatever relation you think is appropriate. But the only thing that we really need is this matrix. We also need some matrices that describe the mortalities, the natural mortality and the fishing mortality. So the simplest one is the natural mortality. I'll describe that first. So we need one matrix that, again, has that standard format. Columns are age classes, rows are intervals or time points during the year. And this matrix just describes what the natural mortality is at each point in time for each age class. So it's really common to set this just to be all the entries here are 1, and we call this matrix little m's. Right, so that's a lowercase ms. There's no reason for that. You could be more complicated if you like. You might, for example, decide that younger fish have a slightly higher, more natural mortality than older fish, and so you might want the earlier columns to be slightly larger than the later columns. But this matrix describes the within year pattern of natural mortality. We also have, and this is kind of inherited from the generalized yield model, we also allow this thing to be scaled. So it's really common to set this matrix all to 1s, and then if you wanted a natural mortality of 0.08, you'd set this scaling to be 0.08. And the logic of this was that for many fisheries, the within year pattern of natural mortality probably doesn't change very much from year to year, but you might want the total mortality to change subtly from year to year. You might want to allow this to vary randomly with a mean of 0.08, but sometimes it's a little larger, sometimes it's a little less. So this little m's matrix, little ms, is the within year pattern that gets scaled by this larger annual constant. In the original generalized yield model, calculations were performed by using the model was solved with a Runge-Kutta ODE solver. We use a different system in the Grym. You can read about it in the vignettes for the package. But one thing we need to provide is a matrix that's essentially, if you think of it, it's really the trapezoidal integrals of this little thing. But if you think of it as the cumulative sums of this little matrix MS, and we call this capital MS, right? Capital M, little s. And if you sort of think of it, it's just sort of the cumulative sum down the rows. So where this might be at this point, this might be the mortality that an animal in age class 2 experiences on day 300. The corresponding entry down here is the total mortality that they've experienced up to day 300. We provide functions for calculating this. It's your responsibility to keep these all coordinated though. You define the lowercase ms matrix, you calculate the capital M, capital MS, you provide the scaling, and you have to combine those in various ways when you call our functions. So the natural mortality is probably the easier one to understand. The fishing mortality mirrors it exactly, but of course it's a little bit more complicated because this within year pattern, you can imagine that you have a fishing season, and so sort of within the fishing season you have fishing, but outside the fishing season the mortality due to fishing is just 0. But within this fishing period here though, you would most likely assume some kind of selectivity, right? So you might sort of assume that the selectivity is something like this and represents the fact that your gear or your whole fishing process is not particularly effective at catching the younger, smaller individuals, and is more effective and are aimed and targeted at the larger, older individuals. And so the chance that a smaller, younger individual will be selected by the gear is sort of small, and that increases for the older individuals. This selectivity can be driven by age, length, or weight. Right? It's up to you how you calculate this. You really just have to provide this matrix where the entries here reflect the mortality that an individual of a particular age experiences on a particular day. Similarly, just like with the natural mortality, we have an overall scaling, F, and we calculate this cumulative fishing mortality. So just as over here for the natural mortalities, if this is the fishing mortality that an individual experiences at that particular time, the corresponding entry over here is the cumulative fishing mortality they've experienced up to that day. Now you need to provide various combinations of these matrices to our functions, and we just adopt a fairly consistent notation, right? These instantaneous mortalities are the lowercase ms and the lowercase fs. The cumulative mortalities is sort of the uppercase ms and the uppercase fs. And then if we apply the scaling, so if we've actually multiplied this m by this lowercase ms, we call that m lowercase ms, right? Or if we'd scaled the other matrix, we'd call that m capital ms, right? And similarly for the f's. And the one final thing we need is sometimes we only need the final row of one of these. And so you might say that f little f s little f, this is, we've applied the scaling to this matrix here of instantaneous mortalities, and the final f is, but we've only kept the final row. So there's this notation that runs through the code. Again, you can read about that in the vignette. You do need to provide all of these things. We provide functions that help you calculate the capital M and the capital Fs from the instantaneous lowercase m, lowercase fs, but you've got to provide those. And essentially the logic is, in a lot of fisheries, those things would be constant, certainly over a very long period of time. And so we don't want to have the code have to recalculate these things. If they're constant, we just want to calculate them once. And so it's kind of up to you to make the decision about what's constant, what's changing. It's totally up to you to keep these keep these coordinated. But if you want to change them from year to year, you're perfectly able to. Okay, so these things are used by the project function. I'm going to talk about this function, but I sort of suspect few people will actually use this. What project does is you give it an initial set of abundances in each age class, and it then projects those forward over the year to give you a matrix N, the abundance in every age class, each age class, every time step of the year. It then uses this weights matrix to just translate that into the equivalent biomass, and we call that matrix B. And all that's happening here is you're saying, I've got this many individuals at this time of this age. An individual of that age at that time should weigh about this. So the total biomass in that age class at that time is this. It's just a translation from abundance to mass. And then finally, we also calculate this yield matrix, right? So again, This is the cumulative catch to this point in time. So if you sort of follow an age class down to this point, this is the total number of individuals removed from the fishery, total biomass of individuals removed from this fishery over that period of the year in that age class. Now, because you rarely want this entire matrix, often you only want that last row. What is the total catch over the entire year? There's an option you can set to project, and it'll either return Y as this full matrix or just the last row, or it won't return it at all. Now, I think many of you probably won't use project in its raw form. There's an alternative function, project C. And the logic here is, instead of asking you to provide a fishing scale, this scaling of fishing mortality, what you provide is the total annual catch. You give that to project C, and what it does is it determines this fishing mortality required to reproduce that annual catch. So you still have to give natural mortality, the within season pattern of fishing variability, fishing effort, and all those other things, but it will calculate for you this scaling of the fishing mortality that gives you the annual catch that you've observed. And I think that's probably what the function that most people would use rather than the raw project function. Okay, so the logic is that you would create this matrix. I think I'll just change color here to sort of emphasize a bit. You'd create this matrix. You'd provide this, 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 and this. You provide the scaling of the natural mortality, but most likely people would, rather than provide this F, they're going to provide the annual catch, and project C is going to combine all of this, do a projection forward over the year that gives us the annual catch we're expecting to see. You then have to call that function many times to project over multiple years. If you want to change the growth relationship, right? So if you could want to change this, you might think that slowly over time, they're growing larger or growing smaller. That's fine. If you want to change the pattern of within year mortality, that's fine too. You just do that on an annual basis. All right. So the next thing for us to talk about is recruitment. Now, we provide several recruitment models. I'm only really going to focus on one. And the thing that's important to remember is that in a model like this, everything's essentially linear. So if you sort of go back to that original picture of time and age, things get recruited to the fishery and they progress forward through time and through age. The thing to understand here is that there's no real density dependence in a model like this. It's all linear. So if we were to double the recruitment and keep all the mortalities the same, effectively everything else doubles, right? Our abundances double, our biomasses and our yields all just double. And so if we double our recruitment, keep the mortalities the same, everything just doubles. If we're using Project C, obviously what that means, if we were to double the recruitment, we'd have to double the annual catch to get the same, for everything else to double. But the basic logic is, once the recruitment doubles, the mortality is the same, everything doubles. And in a model like this, really, your abundances and your biomass are really a tension between recruitment and biomass. So recruitment's really key. The model that we use in the, well, we've been talking about for the krill assessments is a model based on, it's called a proportional recruitment model. It's based on some work by Bill Delamere in 1994. If you want to look up, it's in CCAMLR Science. I think it's the first volume, 94. And it talks about modeling krill recruitment. But essentially the logic of it is this, and people get a little bit confused by this, so I just wanted to go through this a little bit. The logic is that you go out and you perform surveys and you look at, these are meant to be age classes, we look at abundance in different age classes. So we're meant to get surveys of krill, resolve them into age classes. I'm not going to discuss how you do that. I'll leave that up to you. But what we then do is we take one reference age class and compare it to all of the older age classes. And the logic here is if you had no mortality at all, then that profile should essentially look like this. All the age classes are equally abundant because nothing ever dies. And on average, if you have this constant recruitment, if you have very, very high mortality, that profile is going to look like this. Things die out pretty quickly and you tend not to have older individuals. Something in the middle, like this. So what the proportional recruitment model does is it picks one age class. It says, what fraction does this make up of the older, the population that's the same age or older? And then it uses that to essentially estimate the natural mortality. But it also assumes that we do many surveys. So there's just not one survey where we get this fraction of what is this age class to the older individuals. We get several of these. So that then tells us about recruitment variability, right? I'm going to call that sigma squared. But basically we're talking about the variability from looking at multiple surveys, but essentially the rate at which we see decline with age tells us about natural mortality. What it doesn't tell us about, if you sort of think about taking the fraction of individuals in one age class compared to all the individuals of the same age or older, it tells you nothing about the mean recruitment, right? So if the recruitment doubled, essentially that age class, and that age class that we'd chosen as the reference age class was sort of 10% of the whole population. If the recruitment doubled and the whole population doubles, it's still 10%. So this isn't telling us anything about the mean level of recruitment. So often what we do is what's called a per recruit analysis, right, where we assume that the mean recruitment is 1. And then we say, okay, for every recruit, what's the abundance that ends up in the population? What's the biomass? What's the, it's obviously going to be very tiny. But then we scale that up. We say, well, for every recruit we've got, we get this much catch. We have this much abundance out in the population, this much biomass. And if we then said, well, actually, the true recruitment is, 1 million times that, then we just scale all those numbers by 1 million. So the important thing to recognize is that in a lot of our analyses, we're doing a per recruit analysis. We're saying for every recruit that we have, what contribution do we get to the abundance, the biomass, the catch? And that plays well with this proportional recruitment model because it's not telling us about the mean recruitment, it's really telling us about the natural mortality and the variability from year to year in recruitment. So a lot of people get caught up in this because they kind of wonder, where has the mean recruitment level gone? And essentially what we're doing is recognizing that everything's proportional to the mean recruitment. So we're sort of scaling that out and saying, per recruit, what's the solution? And then at some point later in time, we have to scale that up somehow if we're going to talk about what's a reasonable catch. So one of the ways that's done is you might estimate an initial spawning stock biomass, and then say, let's make the catch a certain fraction of that initial spawning stock biomass. And then ultimately, you've got to come up with either an estimate of what the recruitment out in the population, or an estimate of the spawning stock biomass, so that you can then scale your solutions to say, well, we really ought to be getting this catch in tonnes. Anyway, look, I think I've said enough for the moment. I'm going to produce another video where I just work slowly through some example analyses, and we'll produce another few videos that sort of help you get started with the package. Thanks very much for your time, and we'll have a question and answer session scheduled for later.